Thank you. All right. Our next speaker is Harald Woracek from Vienna University of Technology, who will speak on the high energy behavior of Weyl coefficients. Please.
Yeah, thank you very much. And maybe to start with, I should move into the camera and say hi. So thank you for giving me the opportunity to give a talk in this program. I'm very happy to have this possibility also because Canada is far away, and so with these Zoom meetings everything works perfectly. Okay, I have prepared slides as you saw just before. There will be 3 parts, maybe 2, depends on the timing. So first I would like to recall some basic facts about canonical systems. So I wrote on the slide a review which is said far too much. I will just recall some facts which I will need later on. In the second part, I would like to formulate some theorems, some old, some new. And in the last part, if there is time, I would like to say some words on about the proof. This is then not anymore on the slides, but on the blackboard. So yeah, I have to go to the desktop now again, and we'll start with going through the slides. Yes. Okay. So if something happens with the internet connection or you cannot see some things, then please just tell me. I can hear you perfectly. Okay. The first thing I should say is that not everything I will say is really strictly perfectly correct. So from time to time, I just neglect some exceptional cases without writing this on the slides. I will try to not forget saying that it is the case when it is the case, but yeah, so please keep in mind what I give is a basic idea. Some exceptional cases should be treated separately, but okay. Yeah, so canonical systems, I assume that most people here have heard already sometimes about canonical systems, but still I would like to recall what this is and what some basic properties. So a canonical system, we consider a canonical system on the half line. So we have a function h, which is called the Hamiltonian of the system. By the way, can you see my mouse on the screen?
Yes, we can.
Okay, great, perfect. So I can use it as a pointer. So we have a function h defined on the half line. It's called the Hamiltonian, and its values are real 2x2 matrices. So we consider 2-dimensional canonical systems. And this function h, it should have several properties. So first of all, the function h, the values should be symmetric matrices. Then it should not vanish on any set of positive measure. And then it should be locally integrable on the half line as it is written, as it is drawn here. So on every finite interval, it should be a L1 function, but we assume that it is not integrable on the whole half line. So it should be integrable on every finite interval, but not on the whole one. And finally, very important assumption, we assume that h of t is positive semi-definite almost everywhere. Okay, so this is a Hamiltonian, and yeah, now we consider this differential equation here. Y prime of t is equal to c times j times h of t y of t, where j is just the symplectic matrix which is written here, and c is a complex parameter, and it plays the role of the eigenvalue parameter. So this equation here is actually the eigenvalue equation of a certain differential operator, which will come on the next slide. And this differential equation is called the canonical system, the canonical system with Hamiltonian h. Now, with such an equation, we have associated a operator model, and it consists of several ingredients. Like usually, if you have a differential equation, you associate an operator. So we build the Hilbert space. It's not in the straightforward way, but also not far from that. So we call it L2 of h. So the Hamiltonian is given, and then we look at the usual L2 space with the measure h of t dt, if you want, with this matrix measure. So these are all measurable functions such that that integral here is finite. Remember that h is positive semi-definite, so this is always a non-negative integrand. So we can write this down. But we do not take, or we must not take the whole space, but just a certain closed subspace. And I will not, I don't want to go into details here. That would be too technical. And of course, we consider functions equal if they coincide almost everywhere, in the sense that that integral here is 0. You know, so h almost everywhere. Okay, and in this space we have a maximal operator. And since the Hamiltonian h is not necessarily invertible, I cannot write this maximal operator really as an operator. I should rather write it as a graph. And so I write down the graph of the maximal operator. So the graph is all pairs fg such that f prime is equal to j times h times g almost everywhere. And of course, in order to have this well defined, we assume that f has an absolutely continuous representant, and then this f prime here is the derivative almost everywhere of this absolutely continuous representant. So you see that this operator, it fits the equation. Maybe I show you the equation once again. So this is the equation, and this is exactly the eigenvalue equation of this operator, if it were an operator. So, yeah. Okay, and then we have boundary values on the left side, because the Hamiltonian h is integrable at 0. It's integrable on every finite interval, so we can assign boundary values. So if we have an element in the domain of the maximal operator, this f here, then we know, I mean, one can prove that the value f of 0 makes sense. So take the absolutely continuous representant, and then this has a value at 0. And this is a boundary map, and then now we are in position to define a self-adjoint model operator by prescribing one self-adjoint boundary condition. So, and this we call the model operator A of h. So it is, and again I specified by means of its graph. So it is all the set of all pairs in the maximal operator. And we choose some self-adjoint boundary condition, and for convenience we choose this one. So the first component of f at 0 should vanish. So this is the operator model, and I don't want to go into any details about these. The only thing I would like to say, we are coming from the side of operator theory, and then our aim or the task for us is to understand the spectrum of this model operator. So this is our task. Okay, and now how to understand the spectrum of this operator? A very important construction in this respect is the construction of the Weyl coefficient. This was done by Hermann Weyl in I think 1910 or something for Sturm-Liouville equations. So how does this work, this construction? This is a really beautiful construction. So we look at the fundamental solution of the canonical system. So, well, I wrote it down. It's the solution of the initial value problem, which is written here. So, yeah, okay, this is just well, actually, it's the transpose of the fundamental solution of the equation. For technical reasons, we pass to the transpose. So, and I mean, this exists because the function h is L1 on every finite interval. So just by the usual existence and uniqueness theorem, we have a unique solution of this initial value problem. This we call the fundamental solution. And now we make a construction. We look at the action of matrices on the Riemann sphere. I mean, C bar, I understand by C bar the Riemann sphere. And then we look at this, I mean, just by fractional linear transformation. So if you have an invertible matrices, then you can define an action of the invertible matrix on the Riemann sphere just by this. I mean, if C is equal to infinity, then you understand this as A over C, I mean, as usual. So we have this usual action. And now we define for every time t and every eigenvalue parameter C, which is in the open upper half plane. We define the Weyl disk. So we take the fundamental solution of our system and we apply it in the sense of this matrix group action to the closed upper half plane. What we get is a disk, of course, because this is a fractional linear transformation here. So if I apply it to some disk, I mean, this is a half plane, so on the Riemann sphere, it's a disk. Then I get some disk, some disk. And these disks, they have very important properties. Namely, first, they are all contained in the open up in the closed upper half plane. The reason for this is that our Hamiltonian is positive semi-definite. Then they are nested. So if time increases, the disks decrease. The reason for this is that fundamental solutions are kind of multiplicative, and again, our Hamiltonian is positive semi-definite. And the third property, the intersection of this nested family of disks. I mean, what can it be? You have a decreasing family of disks, so the intersection is either a disk or a point, and it is a point. And what is responsible that it is a point? Our assumption that the Hamiltonian is not integrable on the whole half line. So this is responsible that we have only a point. Okay, and now we can define a function. We can define a function which takes as an argument a point in the upper half plane and which maps it to this one point, which is in the intersection of all the Weyl disks when time goes to infinity. And this function is called the Weyl coefficient. So I have written it here. So this function is called the Weyl coefficient. And this function has a very nice property. It is analytic. It is analytic, and obviously it maps the upper half plane into the upper half plane, because I mean, remember, all the Weyl disks are contained in the upper half plane. So the intersection is of course also, but it is analytic. It is analytic. So it is an ever-linear function, or some people rather call it Herklotz function. Of course, it could be identically equal to infinity, but never mind, this is just a boundary case. So it is an ever-linear function, and therefore it has an integral representation. This is well known. I mean, it comes more or less from the Cauchy integral representation of an analytic function, and yeah, so it looks like this. Yeah? So every linear function has a representation of that form. So it is a linear polynomial where the constant coefficient is real, the linear coefficient is non-negative, and then there comes such a kind of regularized Cauchy integral with a measure which is a positive measure, and it is Poisson integrable. So the integral of the measure over 1 plus x squared is finite. So we have these ingredients from the Herklotz integral representation. And now we can formulate a direct spectral theorem. Maybe before you look at the integral transforms up there, you look at the theorem. It tells us that we have an isomorphism between the model space of the canonical system, L2H, and the L2 space of the measure, which appears in the Herklotz integral representation of the Weyl coefficient. And it tells us that the model operator corresponds via this isomorphism to the multiplication operator with the independent variable in this L2 space. So this direct spectral theorem says that the construction of the Weyl coefficient enables us to produce in a deterministic way a spectral measure for the operator. In particular, the operator has simple spectrum and so on. And okay, and now we maybe look at the formulas further up. So not only that there exists an isomorphism, it is actually a nice integral transform. So yeah, the formulas are written here. So as usual, if you define an integral transform on a L2 space, we define it on compactly supported functions, and then you have these two formulas. Yeah, okay, that's how it is. Maybe I should say here that a very simple, well, very simple is the wrong word, a very classical example for a Hamiltonian is the Hamiltonian, which is just the identity on the whole half line. So, I mean, this is, of course, a positive semi-definite, locally integrable, and so on. And if you take for the Hamiltonian just the identity, then the fundamental solution will be a matrix consisting of cosine and sine functions. And these integral transforms here will be just the usual Fourier transform. So the usual cosine and sine transforms. So in this sense, we could think of canonical system theory as a generalization of usual Fourier transform theory. Okay, so this is the direct spectral theorem. Okay, now we also have an inverse spectral theorem, which is a very important point. Namely, I mean, recall what was the procedure to get the direct theorem. We started with our Hamiltonian, then we construct those Weyl disks and so on, then we get the function, the Weyl coefficient, which is a Never-linear function. Okay, and from this Never-linear function, we get the spectral measure and so on. Okay, and now conversely, if we start with a Never-linear function, we can find the Hamiltonian such that this given Never-linear function is the Weyl coefficient. So if you want to formulate it in a little bit more abstract way, you can say that the assignment which assigns to a Hamiltonian its Weyl coefficient is a surjection of the set of all Hamiltonians onto the set of all Never-linear functions. It is surjective. And the second point is that, I mean, it is not injective, but almost. So one can describe the kernel of this assignment in a very explicit and nice way. Maybe I will come to that point later. It is just up to changes of scale. So if you make a transformation of the independent variable, then yeah, everything will be the same. So but this is everything. So the kernel of this assignment is determined by a very well understood thing. Okay, so this is the inverse spectral theorem. So what does this tell us now? This tells us that Hamiltonians and canonical systems and model operators on the one hand and never-linear functions on the other hand are more or less the same. So we can use either viewpoints to study the other object. So if we say, okay, I personally come from the side of operator theory. So as I said before, we want to study the spectrum of the model operator. And studying the spectrum of any simple, any self-adjoint operator with simple spectrum, more or less, I mean, it just amounts to studying canonical systems, because for every self-adjoint operator with simple spectrum, we can construct a Hamiltonian such that the model operator is unitary equivalent to the given one. Even with a finite spectral measure and so on, so it doesn't matter. So studying self-adjoint operators with simple spectrum is more or less the same than studying canonical system. On the other hand, the Weyl coefficient is a never-linear function. This means that it maps the upper half plane analytically into itself. Now, if you imagine you just concatenate with a fractional linear transform, putting the upper half plane to the unit disk, what you get is a function in the unit pole of the disk algebra. So the set of never-linear functions is nothing but up to this fractional transformation, nothing but the unit pole in the disk algebra. So studying this unit pole is more or less just the same than studying canonical systems. So I mean, what you see here is that here we have three viewpoints on one and the same thing. We can either think of self-adjoint operators with simple spectrum, we could think of the unit ball in the disk algebra, or we could think of canonical systems. And this is very interesting because you can prove theorems about one of these three things by using theorems of the others, and so many different tools and ideas can be merged. I should say that what I wrote here as corresponds kind of is highly non-trivial. So usually it is very non-trivial to translate from one to the other. But if one can translate, then it gives something interesting. Okay, so this was a little review about canonical systems and maybe a little advertisement to deal with such. Now I come to the second part of my lecture. As I said before, we are operator theorists, so we want to study spectral properties. I mean, we want to study the measure mu h. Mu h was the measure in the Herklotz integral representation of the Weyl coefficient, and the direct spectral theorem told us that this is a spectral measure for the model operator. And now, I mean, maybe I should show you the formula again. The Herklotz integral representation, where is it? Here it is. This integral representation. So, I mean, just neglect this linear term in front. That's one of the exceptional cases which I usually just neglect. And then what you have is that the Weyl coefficient is a Cauchy integral. Okay, regularized a little bit, but never mind. It's a Cauchy integral of the spectral measure. So, of course, you can translate from the spectral measure to the Weyl coefficient. These are just some classical abelian or Tauberian theorems which tell you that you can translate from the spectral measure to the Cauchy integral. And what I want, I mean, there are many properties you can translate. What I want to focus on today is what some people
Harald, I don't know it's me or not, but I can't hear you.
I can't hear.
Harald, there is something wrong with the sound, I believe, with the microphone. Oh, okay, yeah, so take your time.
Can you hear me now again?
Yes.
Okay, great. Yeah, that was typical. I mean, I gave quite some lectures already with this battery, and of course it must fail exactly now. So, okay, so what was I saying? Ah, yes, the high energy behavior. What is the high energy behavior? This means the behavior of the function towards I infinity. So if we move upwards along the imaginary axis, sometimes non-tangentially, sometimes really on the imaginary axis, but so to say, this behavior is called sometimes high energy behavior. And just by classical theorems, we can translate this behavior often to the behavior of the measure in the Cauchy integral representation, how it behaves at infinity. I've written up some examples for this. What is now? Ah, yes, now it changes. I want to show you again the Herklotz integral representation. It looks like this. So it's a Cauchy integral, a little bit regularized, and then there is some linear term. And then the existence of this linear term is some exceptional situation. Okay. Now, where are the theorems? Here. I mean, these are just some classical stuff. So I wrote 3 of them. So for example, to have a finite measure, okay, and the linear term is not there. Yeah? So to have a finite spectral measure is equivalent that the Weyl coefficient has this lim sub property at infinity. Yeah, so the imaginary part, which is the Poisson integral of the measure mu h, should not grow slow. It should, I mean, it should decay fast. Yeah? That's yeah, so this lim sub should be finite. Okay, so this is I don't know to whom to attribute this. This is just, well, very classical. The second equivalence here is maybe one should read first the right side of the equivalence. So this deals with the asymptotic behavior of the Weyl function. So here, if we move upwards on the imaginary axis, then the Weyl coefficient it behaves like a power asymptotically. Some constant, this omega, this is some non-zero constant, and gamma is some exponent. Yeah, so it behaves asymptotically like a power, and this is equivalent to the measure also behaving asymptotically like a power in the sense which is written up there. So the symmetrized distribution function should really behave like a power asymptotically, and the contribution of the left and right sides, it should not oscillate. Yeah? It should not oscillate too much between left and right sides. So these contributions, they should have a limit, this quotient. So I mean, this is also, I think, this is essentially, it is Hardy Littlewood, I think also 1910 or something, I forgot. So this is also a very classical thing. And okay, so here we have finiteness of the measure, then here we have power, really power asymptotics of the measure. What we have here, I mean, we know that the measure is Poisson integrable. So if I put gamma equal to 2 here, then that will always be finite anyway. What happens in between? So I mean, this is a condition on the measure, integrability, weighted integrability. Also, this can be characterized. It's also classical. I don't know to whom to attribute this, but it's at least from the 60s, so well-known thing. So we have this weighted integrability here, if and only if we have that the Poisson integral, the imaginary part, has this weighted integrability. So you see that one can translate the behavior of the measure at infinity to the behavior of the Cauchy integral at plus I infinity in several ways. And then I should add here, because it will pop up on the next slide or in one but next slide, I should add here that the same theorems hold when the power is replaced by a regularly varying function in Karamata sense. So for those who don't know what regularly varying function is, I will recall it later. But just to tell you that these are not the most general forms of these equivalences that do exist, which I wrote here. Okay. So the message is that studying the spectral measure at infinity amounts to studying the Weyl function upwards along the imaginary axis. And now the task is to relate the properties of the Weyl function to properties of the Hamiltonian. Because, I mean, after all, we want to study the spectrum of the operator of a Hamiltonian. So if you imagine we are given a Hamiltonian, we want to study its spectral measure. Now, studying the spectral measure amounts to studying the Weyl function. So it's enough to translate from the Hamiltonian to the Weyl function. Okay, and then, well, if one starts from an equation and goes to the spectrum, then one speaks of direct spectral theorems or relations. And then if one starts from the spectrum and goes to the equation, one speaks of inverse theorems. And I mean, usually inverse theorems are more difficult, but that's not always true. It can very well happen that the direct theorems are also difficult. So I think there is not much in this theory which is easy. Okay. So this is our task. We want to translate here. Now let us go through these three things that I wrote up, and maybe I should recall it again. So this was finite spectral measure, then really a power asymptotic behavior, and a weighted integrability. So the finite spectral measure is also, well, I don't want to say classical, because I mean the reference I know is of Henrik Winkler from 2000. It's not classical, but I'm pretty sure that the result was known already a long time ago, but I don't know a reference. It tells us that we have a finite spectral measure. Equivalently, the Weyl function satisfies this lim sup condition, if and only if the Hamiltonian starts in a very specific way. The Hamiltonian is a positive semi-definite matrix, and what stands here says that there is an interval at the start, starting from the initial point to somewhere, where this Hamiltonian is more or less, it's kind of constant with determinant 0. So the kernel of the Hamiltonian is constant. Not in an arbitrary direction, but only in a direction which is not the one which is written down here. So this is equivalent to having a finite spectral measure, and just for completeness, to settle once and for all this silly exceptional case of the linear term. To have a linear term in the Weyl function is equivalent that there exists an interval in the beginning where the kernel of the Hamiltonian is equal to this, but okay, so here you see that we can characterize finiteness of the spectral measure very explicitly in terms of the differential equation. Okay, now let me come to the other, to the next. Okay, I will formulate this now actually really for regularly varying functions, and therefore I should recall what a regularly function is. So if we have a measurable function on the half line, then we call it regularly varying at infinity with some index rho, which is a real number, if we have this limit here. So if you imagine that the function f would be just the power x to the rho, then I mean this is the prototype of a regularly varying function, because if f is just the power x to the rho, then well, of course, then everything cancels here, and well, it's lambda to the rho. So regularly varying functions, one can imagine, are functions which behave roughly like a power. Okay. Oh, of course, the same notion you can define at 0 when you just let r tend to 0 instead of infinity. And the same notion you can define when the exponent is plus or minus infinity, just by formally understanding, let's say, lambda to the plus infinity. What is it? It is 0 when lambda is smaller than 1, and it is plus infinity when lambda is larger than 1. So just in the canonical way, if rho is plus or minus infinity, you can use the same formula, and then one speaks of rapidly varying functions. Okay, and now the theorem, which these are the notation and the assumptions. Maybe I should first show you the result. It translates in a if and only if way asymptotic behavior of the Weyl function to a property of the Hamiltonian. So the first statement is the Weyl function has some asymptotic along the imaginary axis upwards, which is some constant times a regularly varying function. So just instead of regularly varying, just think here is a power, r to the rho. So we have these asymptotics, and this is equivalent to 2 to the property 2, and to explain what this is, I will go back on the slide, but this is something which is just explicit in terms of the Hamiltonian. And the third point is just a specific way, I mean, it is just a more exact description of the asymptotic. So, but now let me explain the notation which was written here. So we write the Hamiltonian, it's a symmetric matrix, so we can write it like this. And then the functions mj are just the original functions of the entries of the Hamiltonian. And the function t is the trace, the integral of the trace. So it is, so the trace is h1 plus h2. So the integral of the trace is m1 plus m2. So, okay, and then there come some assumptions. We don't have to read them. Yeah, and then, okay, this function, I mean, this product here is an increasing bijection of the right half line onto itself. And so it has, so the geometric mean has an inverse. And so this function t with a circle up there, it's more or less the 1 over the inverse of something like this, of the geometric mean. Something like this. Now, let's look at the property 2. That makes now perfect sense. So the original functions of the diagonal entries of the Hamiltonian, they should be regularly or rapidly varying at 0. And the off-diagonal should not oscillate. It should not oscillate. It should be such that the limit, this limit which is here, exists. So having a regularly varying asymptotic of the Weyl function is equivalent that the Hamiltonian has the property that its diagonal is regularly varying and the off-diagonal does not oscillate too much. Okay. The third item maybe we don't have to read. It is just for those who maybe are more familiar with these notions, it is just a precise description of how the asymptotic looks. Looks like this. And now maybe I come to the, maybe I should say this, I wrote here, this is work together with Matthias Lange and Raphael Bruckner. And it is unpublished. I mean, there will be an archive version, hopefully very soon, but well, up to now it is not available really. It's more or less finished, but yeah. Okay. Now let's come to weighted integrability. Weighted integrability. This is the theorem. It's again together with Matthias Lange and Raphael Bruckner, and for this theorem there is already an archive version. And okay, what does it say? Yeah. Maybe let me go back to the weighted integrability abelian Tauberian result. If you look here at item C, then here we use the power. We compare the measure and the Weyl function. We compare it with a power. So the weight is a power. And okay, in this theorem, I formulated it again in the proper way. We don't compare it with a power. We compare it with a regularly varying function. But if you imagine, if you imagine here that our regularly, I mean, as I said, regularly varying functions are more or less functions that behave like powers. So if you think that this function f is really just a power, then what you get here in the integral, I mean, it's a power, because if you differentiate the power, you will have a power, and then you divide. So if f is not only regularly varying but really a power, then this will just be a power. Okay, and then so you see that the middle condition number 2 is that the spectral measure is has a weighted integrability property, or equivalently, I mean, here it is written, the Weyl coefficient has a weighted integrability property. And here we have a sufficient condition, number 1, and a necessary condition, number 3. I mean, these are conditions which are obviously explicit in the Hamiltonian. So here is the upper diagonal entry. And then here again, here are the original functions of the diagonal entries. Again, the geometric mean of those two plays an important role. And then here is the function f, which is the weight with respect to which we want to integrate. And here, and then number 3 is the same. It looks only more ugly. So it is not only the left upper entry of the Hamiltonian, so but some mixture of the entries of the Hamiltonian. And again, our weight function. And I mean, here I should say that what holds are these two implications. And what is also true is that condition 3 does not imply condition 1. Yes, but we do not know what would be equivalent to 2. So we have a sufficient and a necessary condition. These two do not coincide, and well, we don't know. We don't know what is really equivalent to 2. I mean, we are working on that, and it seems that there is some hope. But yeah, at present we don't know. Yeah, so you see that one can characterize the spectral behavior of the behavior of the spectral measure towards plus minus infinity. One can characterize it often in a pretty explicit way from the equation. Okay, now maybe I come to another thing. Maybe I go back just briefly to one slide. This one here. Here I explained, or tried to explain, that canonical systems is one viewpoint on the same thing, like self-adjoint operators with simple spectrum, or the unit ball in the disk algebra. So, and all the theorems up to now dealt with the spectrum of the operator. Yeah, because I'm operator theorist, so. But now I thought I would like to also discuss one result which falls in the second category. So it discusses a property of analytic functions on the unit disk. And where is it? Yes, yes, it is this. So it deals with cluster sets. So if you have an analytic function on the unit disk, and you have a point on the boundary of the unit disk, so the circle. And then you look at the radial cluster set. So this is just the set of all points such that you find a sequence that goes to 1, such that the function at these points tends to omega. And denote it like this, the cluster set at the point theta of the function f. And then, I mean, this is a very classical object, which was studied a lot, as I have learned recently. And there is one paper. It is of these 3 people, Bellner, Colville, and Piranian. It's from 85. And they prove an interpolation result. They prove that, okay, if you have a countable subset of the unit circle, and for each point of this countable subset, you prescribe some non-empty closed and connected set. Then you can interpolate it. Then you find an analytic function on the unit disk. It's even a Blaschke product, such that at every point, the cluster set of this Blaschke product at this point is equal to the given set. Obviously here I've changed the notation. I mean, here there was the function inside and the point down, and here it's the other way, but well, never mind. So this is the cluster set of the function f at the point here, the radial cluster set, I should say. So this is an old result. I mean, not so old, but still old. It's an interpolation result, and then we well, we gave a proof recently in a paper with Raphael Bruckner of a much weaker result, but from another perspective, it is stronger, and it connects with the theory of canonical systems. So we interpolated only one point. So we start with some non-empty. Okay, I passed here from the units, from the unit disk to the upper half plane, but okay. So we start with some non-empty closed and connected subset of the closed upper half plane, closure on the Riemann sphere, of course. And then we find the Hamiltonian such that the cluster set of the Weyl function, if I radially, so if I go to infinity along the imaginary axis, is equal to this pre-given set. I mean, the existence of this is in view of the theorem of Bellner-Cordell-Piranian a triviality, but what we do is that we actually construct the Hamiltonian explicitly. We construct the Hamiltonian explicitly, which is a very nice construction. And actually, I've prepared the proof of this theorem as a proof I wanted to present you, but if I look at the time, that will not happen. So maybe I should just close with one question, open question. I have already communicated with some people. So if we look not at radial cluster sets, but at non-tangential, so outer angular cluster sets, it is called. If we look at that, so it is the set of all points such that we find a sequence that non-tangentially tends. So not radially, but non-tangentially tends to this boundary point, and then yeah, it's this limit point. Then it is obvious, more or less, that every set of this form is an increasing countable union of non-empty closed and connected sets. And the conjecture is, I mean, I don't even know if it is a conjecture. I've just asked around and some people said it's not known. So maybe if somebody of you knows that this is true or false, then please let me know. In any case, Paul Gautier, I communicated with him some months ago, said that he has a proof that the converse holds. So for every increasing countable union of non-empty closed connected sets, there exists an analytic function in the unit disks which has this outer angular cluster set. But he told me this, and a couple of weeks later he told me that he found a gap in the proof. So it is still a conjecture, at least up to my knowledge. And okay, I mean, our idea to give a proof would be to well, not only construct the function, but actually construct the Hamiltonian such that the Weyl coefficient has exactly this outer angular cluster set, and yeah, that would be a nice result. But we have honestly no idea how to prove it. Okay, so I think my time is well, perfectly up without showing any proofs, unfortunately. Maybe another time I can speak about the proof of one or the other theorem I presented today. Okay, so maybe now I switch to the camera again. No, how does it work? Yes, I switch to the camera again, and I may ask you. Yeah, I thank you for your attention, of course, and yeah, I may ask you for questions or remarks or whatever. Yeah, thank you.
Very much. So yes, questions, comments. So
there is a question in the chat.
Yeah. In which space does the function f belong?
Sorry?
To which space does the function f belong?
The function f in which just a second, I switch back to the slides. In which theorem? Here or?
Yeah, in the conjecture, in fact.
Yes, in the conjecture, in fact. Sorry, yes. It should be analytic on the unit disk and bounded by 1.
Okay, thank you.
I mean, in the theorem of Bellner, Kolbel, and Peranian, it is a Blaschke product that they construct. In our theorem, actually, it's also a Blaschke product. So in the conjecture, maybe it also could be a Blaschke product. I don't know. I mean, I don't know if the conjecture holds at all. But yeah, basically, it is just a function, the analytic on the unit disk bounded by 1.
Other questions? Jawad?
Yeah, no, I don't have questions.
Okay. All right. So, okay, so if there aren't any questions, then let's thank our speaker again. Thank you very much for a very interesting talk. And,
yeah, thank you for attending.
Thank you.